Hi everyone. In the previous class, we have seen the concept of adders, subtractors, and also we have seen how to perform both addition as well as subtraction in the same circuit. I hope you understood everything clearly. Okay. Now in today's class, we'll see the concept of how to perform multiplication. Right? So means when you are going to have uh, two 1-bit numbers, how you are going to perform, right? So generally you are going to have the decimal numbers like 5 and 6. How we are going to do 5 into 60 is 30. Similarly, when you are going to have two numbers, one is a, another one is b, another one is b, you can perform, right? One is 0, another one is 0, your result will be 0. One is 0, another one is 1, then your multiplication will be 0. One is 1, another one is 0, your result will be also 0. One is 1, another one is 1, then your result will be 1. So this is what the 1-bit multiplication. So if you are able to solve this truth table, you are going to get like this, right? So you can able to simply use basic evaluation, or you can able to use schema approach, where you can able to solve the equation for this one, right? So if you would like to perform multiplication for two inputs two inputs a and b, you need to use a simple AND gate where each a and b are data, right? You are going to get the result. Fine. Similarly, you can have 2-bit number, right? So if you are going to take one number as a0, another number as a1, and one number as b0, another number as b1, right? If you would like to perform multiplication of these two numbers, how we are going to do, right? Basically it look like this one, right? 12 multiply with 13, right? So first 3 into 2 6, 3 ones are 3, 1 into 2 2, 1 ones are 1, then basically you are going to get 156 as the answer, right? The same procedure here also going to do, right? So when you are going to perform multiplication here, you are going to take b naught multiply with a naught, b naught multiply with a naught. Okay, and the same thing you are going to do b naught multiply with a1, right? Similarly, after completion of the single number, you are going to take the next number, right? b1 should be multiplied with a naught, but the next level, how we are going to do, you are going to shift one location and you are going to write, that is b1 a naught, and what about another one, b1 a1, right? All the things are completed. So this is what I am going to do. Finally I am trying to perform some operation. So your result will be, uh, I can say that it as p naught. I can say it as p naught, meaning that p naught means it will be like a naught b naught, and I can call this as p1. I can call this as p1. P1 means it will be a1 b naught plus a naught b1 plus, and guys, is there any carry is going to produce here? Is there any chance to produce the carry? No, because here you are going to get only one bit of number, so you won't get any carry. That's the reason there won't be carry for the p1. There won't be carry for the p1, meaning that p1 is not depend upon any carry. Okay, let me try to get the next number, that is p2. How we are going to get p2? P2 are going to get because of a1 b1 plus, guys, as here you are trying to perform addition of two numbers, this may get chance to generate a carry, so I can write it as carry of p1, carry of p1, right? P2 means a1 b1 plus carry of p1. Now this carry and a1 b1, if it is going to add, then you may get a chance of another carry, that is p3. So p3 is simply carry of p2. Okay, fine. Means when you are going to have a multiplicand called a1 a0 and a multiplier called b1 and b0, you are going to simply take the one bit of multiplier, and you are going to perform multiply with all bits of the multiplicand, all bits of the multiplicand. And when you are trying to take the next bit of the multiplier, you are going to shift one bit, and then you are going to perform multiplication, right? Guys, if assume that in the multiplier, if the selected bit is a 0, then we are going to simply place all the zeros, right? If the selected bit is 1 from the multiplier, the multiplicand, after performing operation, you are going to get the result as multiplicand. Am I right? See, meaning that what I am trying to say na, when you are going to perform uh, 1 0 multiply with 0 1, right? This is what multiplicand I can call it as m, and this is what multiplier I can call it as q, assume, right? Now when I am going to select a multiplier as 1, what is its result? The result will be same as it is as multiplicand. That is what 1 into 0 is 0, 1 into 1 is 1. And you are going to select the next bit, that is 0, and when you are trying to get the multiplier bit as 0, you are going to get all zeros. All 0 means how many number of bits are there in the m, that is number of zeros, right? But when you are trying to write in the next location, it should be shifted towards this one, right? Now we can able to perform the addition. This is 0, 1 0 is 1, and this one is 0 1 0 as the answer, right? Now in decimal, what is 1 0? I think 2. In 0 1, number is 1. 2 into 1 is 2, which is equivalent to again 0 1 0 2. I hope you understood, right? Yes, fine. So guys, here we have a the requirement resource we got, that we analyzed, and from that analyzation we tried to derive the expressions, that is p0, p1, p2, p3, right? So meaning that this is one kind of partial product. Am I right? So this entire line I can call it as one partial product, meaning that to get this sum you need to have n partial products. N partial products means how many number of bits are there in the multiplier, that many number of partial products are available for me. Okay, fine. So now I will try to construct circuit for you. So assume that I am going to have 4 bits. Those 4 bits are, one is a naught, and so I can make b naught as adjacent, so it will be easy for circuit. A naught, b naught are available, so I can make like this, a naught, b naught. Then you are going to get p naught as output, right? Yes. So simple and get. Similarly, to get p1, what you require? You require a1 b naught as well as a naught b1. A naught b1, a naught b1 is you are going to perform AND operation. Good. And a1 b naught, it is going to perform again an AND operation, right? And guys, try to observe, this is going to produce one number, that is a0 b1, and this is going to produce a1 b2 b naught. Now these two numbers has to be add, right? This is not like OR operator. These two numbers has to be add. So to make adding of these two numbers, can I able to use, as I am going to have 2 bits, as I am going to have, this is 1 bit, this is 1 bit, 2 bits, can I able to use one half adder? Yes, I can able to use one half adder. So where if I am saying that it's a half adder, it is going to perform addition of only 2 bits. So I can give one input as a0 b1, another input as a1 b0. Then it is going to produce P1 as output. P1 as output means what? Indirectly I am saying that sum of two given inputs. Right? For this half adder, one carry is going to be generated. Right? So you know. Now to get P2, first I need to perform A1 B1 multiplication. A1 B1 multiplication I have to do. Yes, I did. A1 B1. Now A1 B1 need to perform addition with carry of P1. You know carry of P1 is coming from here. So now to perform 2 bits addition, can I go for simply one more half adder? Yes. So this is 1 bit as input, and carry is 1 bit as input, right? Now you are going to get sum as output, I can call it as P2, and which is going to generate once again a carry. That carry I can call it as P3. That's P3, right? So meaning that if you are going to have A1 A0 and B2 B1 B0, your result will be simply P through P2 P1 P0. Okay, fine. Similarly, you can able to perform multiplication operation for 4-bit binary multiplier like that, right? So when we are going to have 4 bits as multiplier, 4 bits as multiplier, I can say that B0, B1, B2 and B3. That should be multiplied with A0, A1, A2 and A3. So you have to do multiplication. So you are going to get 4 levels, 1, 2, 3, 4 levels, and finally you are going to get its sum. So sum will be I think so when you are going to perform 2 n bit numbers, you are going to get 2n bits. You are going to get 2n bit, right? So I hope you know, right? So that will be P0, P1, P2, P3, P4, P5, P6, P7 and P8. So for this 8 bits you have to construct the circuit. Okay, guys, if you are able to observe here, so it's a kind of some lengthy procedure or not? Yes, it's a kind of complete lengthy procedure. So that's the reason we can go for uh, uh, see, are you going to get here P0 to P8 or P0 to P7? So here you are going to get only P0 to P7 number, right? Because you are going to get only 8 bits, P0 to P7. Okay, fine. If you are able to observe here, this is something like kind of lengthy process. So instead of this one, so they have gone for one kind of method. That method is a register shift method, which is a simple process compared to the previous procedures, right? So what they are trying to do here, for example, let me try to do 1011 is going to multiply with 1010, 1010, right? Yes, so you can take like 0 multiply with 4 1 like 1011, you can make it as 4 zeros, right? 1, so you can shift 1 bit, 1011. Next 4 zeros, you can do like this, right? Next you can multiply with 1, so you will get 10 double. Finally, if you are going to perform addition of the respective things, you will get 0 1 1 1, I think 1 0, sorry, this should be 1, this should be 1, right? Double 1 double 1 0, triple 1 0. Okay, guys, is there any change, right? Is multiplication is commutative or not? Yes. So if you are going to take 1010 into 1011, are you going to get the same result or are you going to get a different result? We are going to get the same result. Because of the reason, I can say that multiplication is commutative in nature. Multiplication is commutative in nature, right? Yes. So try to observe. I will do some process. See, final resultant bit contains, final resultant relation contains maximum of 8 bits. Am I right? That is what I said, right? Final resultant relation contains maximum of 8 bits. Maximum of 8 bits, right? If I am going to say that the result contains maximum of 8 bits, so I am going to take here one 8-bit register, right? Where it contains default, I am going to place all zeros, 3, 3, 6, 7 and 8. 7, 8, right? So guys, now try to observe. The point here is I am trying to multiply 1010 with 1011. So I am going to make this as M and this as Q. Technically, I can call this as a multiplicand and this as multiplier. Right? Now I will do parallelly. When you are trying to multiply with 1, what you are going to get? You are going to get 1 0 1 0 1 0 1 0, right? So now here also I will try to take 1 and I am going to multiply with 1 0 1 0 1 0 1 0, right? Now this 1 0 1 0 I am going to add to the MSB bits, to the MSB bits of the register. So this is 8-bit register 1010, right? So when you try to do perform addition, what you are going to get? You are going to get 1010 followed by 4 zeros, followed by 4 zeros. So I did addition, I did addition, right? After performing addition, you have to make right shift. You have to make right shift. Why I am trying to make right shift? Try to observe. If I am going to multiply with 1, if I am going to multiply with 1, what you are going to get again? 1 0 1 0 1 0 1 0, right? So try to observe right shift. If I am going to perform right shift, all bits are moved towards right shift by 1 bit, right? So then you will get at the side 0. So this one will be moved to here, this one will be moved to here, this one will be moved to here, and this 0 will be comes to here, and all the things, right? 3 3 6 and 8. So total like this 0 1 0 1 4 zeros. Now after this one, try to do. So now what I am trying to do, you are trying to perform multiply with once again 1. When you are trying to perform multiply with once again 1, I can simply add 1 0 1 0 1 0 1 0. Guys, try to observe, is this one. So I will make simply here 0 0 1 0 1 0. If you are able to observe, this is 0 1 0 1 0. Am I making like adding of 1 0 1 0 or not? Yes. Is these two structures are same or not? Yes. Yes. That's the reason I am going to first perform addition, then I am going to perform right shift. Then I am trying to perform once again the addition. If you are going to get here all 4 ones followed by 4 zeros. Then after this addition, you have to perform once again a right shift. When you right shift, you are going to get 0 followed by 4 ones followed by 3 zeros, followed by 3 zeros, right? Now try to do with 0. Try to do with 0. When you are going to do with 0, you are going to get all 4 zeros. Okay, here also you are going to get all 4 zeros, and you are going to get the result as 0 4 ones followed by triple 0. So you did performance of addition. After performing addition, you have to perform right shift, right? 0 0 4 ones double 0. So this is what I can say it as a right shift. Right shift. Similarly, I am going to perform multiply with 1. So you are going to get 1 0 1 0 1 0 1 0, right? Now if I am going to perform multiplication with 1 0 1 0, that result I am going to add it here. So you are going to get, think here it is 1, here it will be 1 0 1 1, and all the remaining thing will be as it is, right? So finally you are going to did addition. You are going to do addition, right? Guys, now is there any need to move? Is there any need to perform right shift operation? Because perform the right shift operation or not? Yes. So here you have to perform the right shift operation. If you are going to perform right shift operation, you are going to get 0 1 1 0 1 1 0 0. So this will be like this, right? So because this rightmost bit will be removed, so you are going to get 0 1 1 0 1 1 0. So this is you are going to get after right shift operation. The same thing, you are going to perform addition, you will get 0 1 1 1, you are going to get 1 0 1, right? The result will be same. So I can say that these two methods are in similarity in nature, right? But the thing is here, trying to construct this particular procedure is a somewhat difficult process, right? So that's the reason they have gone for this kind of procedure, right? See what I did now. Let me take for example one more number. Let me take for your understandability, I'm trying to multiply with 0 1 0 1 with 0 1 1 0 0 1 1 0, right? Now what you can do, simply you can simply create one register. So as multiplicand contains 4 bits, multiplier contains 4 bits, your result will get 8, maximum of 8 bits, right? So 1 2 3 4 5 6 7 and 8. Now what you can do now, when you are trying to perform multiplication with 0, multiplication with 0, simply make add that number of zeros. You are going to get 4 zeros followed by again 4 zeros. Okay, now after that you have to perform addition. Right? So means observe, when you are going to get simply 0 as one of the bit of the multiplier, you can simply perform right shift. Is there any necessity to perform again adding and getting the result and try to right shift? No, because it is equivalent to again the same result. So that's the reason what you can do now. When you are going to get 0, you can simply perform the right shift. Right? So as in this case, all are 0. There is no need not necessary for right shift also. But when you are going to get 1, you need to perform addition. Along with addition, you need to perform a right shift operation. Okay, fine. So guys, here next we'll try to multiply it with 1. When you try to multiply it with 1, you are going to get 0 1 0 1. So you can simply add it to here 0 1 0 1, and this result you can able to make it a right shift, right? So what you can do here, I will try to make the directly process. So I will get 0 1 0 1. So what I will do, I will try to perform right shift 0 0 0 0 1 0 1 triple 0. I hope you understood, right? I did both addition as well as right shift. So this one done. Now similarly for the another one, you have to add 0 1 0 1 0 1 0 1. So you are going to get 0 4 ones triple 0. Now perform right shift. When you try to perform right shift, 0 0 4 ones will be as usual and double 0 right shift. Now when you get 0, what you can do, is there an necessity to perform the addition? No need, just you can make it right shift. When you make it right shift, you are going to get triple 0 followed by 4 ones 0. This is the result you need to have. Guys, if you observe here, the value of this one is 1 2 4 4 5 5, and this one is 6 5 6 are 30, right? So your result should be 30. Try to do this one. 1 2 4 8 16. 16 plus 8 24. 24 plus 4 28. 28 plus 2, which is equivalent to 30, right? Both procedures are same, right? Okay, fine. Guys, this particular procedure having an advantage, meaning that when you are going to get zeros, you will simply perform right shift operation. When you are going to get 1, you are going to perform addition as well as right shift operation. I mean, if you are going to have uh, two n-bit numbers, and that n-bit number, if one of it is multiplier, right? Yes, this is purely we did because of multiplier only, right? We are saying that this is based on the multiplier. If multiplier is 0, then I'm going to simply perform right shift. If multiplier is 1, I'm going to perform addition as well as right shift. So if multiplier contains n bits, we need to perform compulsory n right shifts. Am I right? Irrespective of whether it is 0 or whether it is 1, compulsory I need to perform n right shifts. Okay, fine. And how many additions we have to do? For example, if I say that m number of ones are available, then you have to perform m additions. This is what you have to do. Okay, so this particular procedure I can call it as register shift method. Right? Now my question is there any particular procedure where we can able to reduce this particular number? That is my question. Okay, fine. That we'll see in the next class.